Good morning to all. Myself, Dr. Jailishmi. I'm working as Associate Professor in the CE Department, SSM Chemical. So, myself, I'm going to give a brief note on MOSFET introduction. So, completely, we are going to have a detail on working of MOSFET. So, let's enter into the topic. MOSFET. So MOSFET, all you might know, it is a semiconductor electronic devices. So this MOSFET or semiconductor devices which play a very important role for switching operation as well as an amplifier also it is going to be used in non-electronic circuits. So what is the major difference between this MOSFET and BJT is BJT is a current control device whereas this MOSFET is a voltage control device. So the main advantage of this MOSFET is it requires no input current to control the load current. This is the major difference between BJT and MOSFET. So for most of the industrial applications in VLSI based industries, this MOSFET is preferred over. And what are the drawbacks when we are going to compare with the JFET? The JFET is going to have only slow operations. Its input impedance is going to be very moderate and it is going to have high drain resistance. So these are all some of the drawbacks of JFET, and these four drawbacks are also overcome in the MOSFET. So coming to the types of MOSFET, there are two types of MOSFET based on the mode of operation. So we can classify the mode of operation into enhancement mode and depletion mode. I will explain you brief in the forthcoming slide. And this enhancement mode again it is classified into P-channel enhancement mode MOSFET and N-channel enhancement mode MOSFET. Similarly, the depletion mode can be classified into P-channel depletion MOSFET and N-channel depletion MOSFET. So this was the symbol used for both enhancement as well as depletion mode MOSFET. So the enhancement mode, this is the symbol, and the depletion mode, this was a symbol for depletion mode. So what is the major difference between this enhancement mode and depletion mode is enhancement mode, it works with positive gate voltage. That is, in short, we can say like that. If you are going to provide a voltage on the gate terminal of a transistor, right, this max, when you're going to increase this gate voltage, and then the current will also be increased. So they are directly proportional. If the voltage applied on the gate increases, then the current also increases. This type of mode is called enhancement mode. Whereas in the depletion mode, just reverse to enhancement mode, even with negative gate source voltages, the MOSFET will operate. That is depletion mode. And coming into the detail of about MOSFET structure. So the MOSFET, first it comprises of in the construction wise, we can say that totally it is going to have three terminals: source, gate, and the drain. Right. So here we can say that MOSFET base. This is called as MOSFET base. I have written here no. The MOSFET base is made up of P-type semiconductor. This part, I'm saying this part. So this part is the base of MOSFET. So initially we are going to take a P-type substrate, so which is also called as body of MOSFET, right? And in this substrate, we are going to diffuse a heavily doped N-type semiconductor material in the two ends, in the two right corner and right corner end. And these first N plus region, it represents the source region, and this part represents the drain region. So we are going to take the terminal, source and drain region with the help of the metal layers. Okay, that was shown in black color. And in the center part, initially we are going to deposit from the upon the base, we are going to deposit SiO2 layer, right? And in above SiO2 layer, we are going to deposit a polysilicon layer, and from that the metal is being deposited, and we are going to take the gate terminal. So totally there are three terminals: source, gate, drain. Okay, so this was the construction of MOSFET. And what is the major difference between this FET and MOSFET is silicon dioxide layer. Okay, layer of silicon dioxide is applied to the substrate layer, as I said previous. So this was the main difference between FET and MOSFET, and that was absent in FET. Only in MOSFET this SiO2 layer is present, and so it is also called as FET with the insulated gate or insulated gate field effect transistor. Okay, so just construction only I have explained. Okay, and how this channel is formed, how the current flows between source and drain, that I will explain in the succeeding slides. Okay, so coming to the FET. So what is the major thing here we are going to see in the MOSFET is here it is going to operate only with the DC voltage level only. So we can the DC circuit is formed once if you are going to apply voltage upon the gate terminal. Only we are this region plays this terminal plays a very important role. We are going to provide the gate source voltage with only in this point. Okay, with respect to the source, we are going to provide VGS voltage only to this point, and this voltage, the voltage which is applied on this gate terminal, it is going to play a very important role in current connection based on the proportionality, or we can say that based on the amount of gate source voltage applied across this terminal, the current will flows. Okay, if VGS increases, the current will also increases with respect to the drain source voltage. That we'll see later. Okay, so here we can coming to the working principle. Coming to the working principle of this MOSFET, the main working principle of MOSFET is the ability to control the current as well as voltage between source and drain, and that happens only with the help of the voltage which is applied on the gate terminal. So, okay, so that is the main reason. If you have whatever the voltage which is applied on the gate terminal with respect to drain source voltage, it is going to completely control the current flow as well as voltage between these two source and drain terminal. Okay, so that is the main thing, and most this MOSFET, it mainly depends on the gate terminal and the capacitance effect that is present only on the gate terminal. Okay, so that is being given here, and generally this MOSFET, it is going to operate under three modes: accumulation mode, depletion mode, inversion mode. Okay, first coming to the first mode, accumulation mode. So as already I said, so this was the substrate layer upon which we are going to place SiO2, upon which we are going to deposit polysilicon layer, and using this metal, this block square box, it represents black metals, and this metals through this metals only we are going to take the three terminal like source, gate and drain. So what happens in this accumulation mode is, here the gate source voltage is not, we are not going to provide any gate source voltage, it is equal to 0, and at the same time the drain source voltage is also equal to 0. So we are not going to provide any voltage to this MOSFET. Under this condition, what happened inside that we are going to see. So as I said, this MOSFET, accumulation MOSFET, this layer is made up of p-type semiconductor material. So the majority carriers of this p-type semiconductor material is holes. So we can say that this this left corner part represents the source region, and this right corner part represents the drain region. And in the between this source and drain, it is completely accumulated of charge carriers that two holes are deposited, because the p-type semiconductor material is mainly used as substrate for this MOSFET. So the majority carriers in this p-type semiconductor material is holes. So completely the holes are accumulated in this particular region, and that's why this mode is called accumulation mode. And in this mode there is no current flow, since no electrons from the source and the drain are going to move. They are going to be still we are going to be in the idle position, since we are not going to provide any VGS or VDS voltage across this transistor. Come to the second mode. This is called as depletion mode. So the word depletion means it is that is depleted. That means there is no any charge carrier. There is no charge carrier. So we can say that here in the depletion mode, okay, in the depletion mode, we can say that here the gate source voltage is going to be greater than 0, but it is provided somewhat less than threshold voltage. So what this threshold voltage denotes is the voltage, minimum voltage required for this MOSFET to conduct. Okay, that is the limit threshold voltage. So if you are going to provide the gate source voltage which is less than threshold voltage, this MOSFET, it is going to operate in the depletion mode. So what happens inside, if gate source voltage is given across this gate terminal, but it is very low, yeah, here it is less than VT, so we are going to provide a gate source voltage which is less than VT, since it is positive voltage. Okay, this positive pulse which is nearer to this region, I am showing that just showing in the cursor, just listen that. So here the holes which are deposited here, that is going to be repelled by this positive gate source voltage, and it is pushed down. So as a result, this layer, that empty balls, no, that represents that there is no charge carriers. Okay, this negative, this minus symbol represents electrons, and this plus symbol represents holes, and these empty, this circle represents, empty circle represents there is no charge carriers. So it is completely depleted of charge carriers due to the repulsion between the positive gate voltage as well as the positive holes. So since this region is completely depleted of this charge carriers, that is holes, it is called as depletion mode. And coming to the third region of mode of operation, that is inversion mode. Here we are going to increase our gate source voltage, which is greater than threshold voltage. So what happened? High gate source voltage, which is positive now. So this positive gate source voltage is given across the gate. So what happens instead? This strong positive gate source voltage will create a strong electric field across this polysilicon region. As a result, it will create a strong electric field in this region. So what happens in this is that this strong electric field, it starts to attract the minority carriers which is present in this p-type semiconductor material. Generally, p-type semiconductor material has majority carriers as holes and minority carriers as electrons. So they are randomly distributed, and these electrons are being attracted towards the gate terminal. Okay, and as a result, a layer of negative electrons will be deposited near below the gate terminal, and since initially it is with positive holes, now it is with negative electrons now. So that is why this mode is called as inversion mode. Okay, these are the three modes of operation. And coming to the operating regions of Mosfet, so this Mosfet, it is going to operate in three regions: cutoff region, ohmic region or non-saturation region, and the third one is saturation region. Okay, so let's see into this first region, cutoff region. The voltage condition for this cutoff region is gate source voltage less than threshold voltage and drain source voltage is equal to 0. So if you are going to give gate source voltage which is less than less than threshold voltage, then definitely there will not be any current flow, because the transistor will not conduct. As a result, the current flow is going to be 0, and simply we can say that in the cutoff region, this MOSFET is merely going to act like a open switch. Only if it conducts, it comes to closed switch condition, else it is in the open switch condition. So we can say that it is in the off state. Okay, MOSFET is in off state when it is operating in the cutoff region. Now coming into the ohmic region, it is also called as non-saturation region or linear region. Okay, here we are going to increase our gate source voltage, and at the same time we are also going to increase the drain source voltage. Okay, see, previous one it is equal to 0, no, VDS is equal to 0, but in this case here we are going to provide some drain source voltage, but it is less than VGS minus VT, but gate source voltage is increased greater than VT. Okay, so what happens in this, that when VDS is increased, okay, so if you are going to increase this VDS voltage as well as VGS voltage, definitely the current will also be increased. Okay, so this is the thing happens. We can see in the diagram itself. So the first cutoff, that is cutoff region is shown here. Here VGS equal to 0, so there is no current flow. Simply there is no channel. Okay, and that is the first region. Now coming to the linear or ohmic region, here we are going to provide gate source voltage, okay, which is greater than VT, and at the same time we are going to provide drain source voltage across this drain terminal. So what happens is that, so this is positive drain source voltage, and this is N plus is negative. No, this drain terminal is made up of it is completely comprises of heavily doped N-type electrons, right? So this is negatively charged. So as a result, the reverse biasing will be increased. So this is if you are going to provide positive voltage to a negative material, that is nothing but reverse biasing. No? So reverse biasing across the drain region will be increased. So as a result, the depletion region. So I am showing now this empty white region that represents the depletion region which is created between this substrate as well as the drain and the source region. So only at the drain end this depletion region will increases, since the reverse bias increases across this region. Okay, so this in this region we are the current, when we are going to increase VGS, which is greater than VD, the current current also increases to a certain level. So they are linearly proportional to each other. That is, the gate source voltage as well as the drain current are linearly proportional to each other. If you are going to increase gate source voltage, definitely the drain current will also be increased. Okay, so that is ohmic region or linear region, we can say. Okay, it is also called as non-saturation region. And coming to the third region, saturation region. The condition for this voltage condition for this region is gate source voltage is greater than Vt, similar to non-saturation region. And the difference is here we are going to increase the drain source voltage, which is greater than Vgs minus Vt. Okay, so that is very important condition here. In this condition, in this region only, this pinch off condition will occur in the transistor. So what this pinch off condition is, so here we are going to increase our VDS. So if once VDS increases, reverse voltage also increases. As a result, the depletion region will, it starts increasing, and at a certain point, I am showing the cursor now. So at this point, the channel will be cut off. Okay. So generally, I have said to you in the inversion mode, this is made up of the negative electrons will be deposited below the gate terminal. This region is going to act as a channel because here negative electrons, here also negative electrons, here also negative electrons. Also, this region is going to behave like a single region, and this is the path. It is going to behave like a path. We can call this as channel. Okay, channel through which the electrons, majority carrier electrons from the source, it is going to move towards the drain. As a result, the current starts to flow from drain to the source. Okay, so that's why this is called as N-channel enhancement, because the channel is made up of N-type semiconductor material, right? So it is called as N-channel enhancement MOSFET. Why I have said this is, this N-channel is formed between the source and the drain. Okay, so this region is channel, and coming to this last region, saturation region, that channel region is going to be cut off. Okay, it is going to be cut off because of this increased depletion region with the near the drain terminal. Okay, so at which voltage, at which value of this VDS, this channel is going to be cut off. That voltage is called as pinch off voltage. Okay, and this region condition is called pinch off condition. Okay, and once if this condition occurs, the drain current which is flowing from source to drain, it is going to be saturated. It is not going to respond to the voltage given across the drain terminal, right? So what happens is that it is being saturated. So whatever, if you are after this, once this condition occurs, even though if you are going to increase VDS, the drain current will not respond to the drain source voltage. It is completely saturated. Okay, it is going to flow constant. That is why it is called as saturation region. Okay, the current is going to remain constant even if VDS increases. Okay, and this region is nothing but saturation region. Now coming to the characteristics of MOSFET. So this MOSFET is going to operate in two, so we can measure the performance of MOSFET, and based on that we have two characteristics: drain characteristics, transfer characteristics. The first one shows the drain characteristics. As I have said to you already, this MOSFET is going to operate under three regions, that is cutoff region, ohmic region or non-saturation region, and saturation region. Okay, so this drain characteristics is drawn between drain source voltage VDS along x-axis and drain current along y-axis. So what happens? We are going to provide gate source voltage. Okay, constantly we are going to increase the gate source voltage. When VGS voltage is equal to 0, it is going to operate in the cutoff region, right? So the current is not going to flow in this. So it is very minute current. Okay, so this region is nothing but cutoff region, since the current flow is 0 here. Here VGS is also going to be 0. Now we are going to increase the gate source voltage, okay, constantly, and we are going to measure the current. So we can say that the current increases, initially it increases linearly. See if the voltage increases, the current also increases. If voltage increases, the current also increases. So this is measured for different values of VGS, and this region where it is, they are linearly proportional. If VDS increases, the drain current idea also increases now. So this linear region is called as ohmic region or non-saturation region or linear region. Okay, and certainly if after this condition, if that is, if we are going to increase VDS to a certain extent beyond this limit, definitely by increasing VGS, the current is going to remain constant. That is shown for each values of VGS. We can say that all these currents are going to remain constant. So this region is completely called as saturation region. As I said earlier, so in the saturation region, the drain current is completely going to remain constant. It is being saturated. It is not going to depend on the VGS or the VDS. Okay. So that is drain characteristics. And the second characteristics, transfer characteristics. So here the transfer character, this is the transfer characteristics of MOSFET. So here we are for enhancement as well as depletion, the graph is shown. So it is drawn between drain source voltage VDS as well as drain current along y-axis. So we can say that if VDS increases, the current ID also increases in the case of enhancement mode, whereas in the case of depletion mode, if VDS increases, the current distorts decreasing. But you should note that this voltage is of negative voltage. So as I said earlier, for the depletion mode, even with negative gate source voltage, the transistor will operate. So this voltage represents negative. So here you're going to have a negative gate source voltage. With respect to that, the current starts decreasing and reaches to a zero value. Okay, and that is at this point the gate source voltage is completely going to be zero. It is called offset voltage. Okay, so this represents the transfer characteristics of MOSFET. And finally, we are discussing about the advantages of MOSFET. The MOSFET have higher efficiency when compared with BJT or JFET, and the input impedance is very high, resulting in a high switching speed, and it is very has low cost, and finally low power consumption. Okay, these are all the advantages. And coming to the applications, it finds application in radio frequency, DC motors, chopper circuits, analog switching devices, and the auto intensity control of streetlights. It's also done using this MOSFET. So thank you for patient listening.